Hello and welcome back to Mrs. O'Graham's Maths. We are going through the D&D Resources for Probability Concepts Level 3 in this video. So first of all, a thank you to D&D Resources for allowing me to use their materials in this way. I have put a link to their website in the description for this video, and I highly recommend that you order a paper copy of these books to work through as really useful exam prep. So let's get started on this one. It's practice external assessment number 2 from the workbook. Now in question 1, we've been given some information about car crashes, and this was from the Ministry of Transport. We've got all of this information here in this table. We have times that the crashes happened and the days that they happened on. First question, if a random fatal crash involving speed is selected from this period, what is the probability that it occurred in the weekend? So let's identify the total that we've got happening in the weekend. So that's 65 plus 48. So that's 113 out of our total of 292, which we usually express probabilities as decimals in this standard. For part 2, if we've selected 2 crashes from this group of crashes, we want to calculate the probability that only one of those 2 occurred during the week. So if we think about this as being crash 1 and crash 2, I like to think of this as a tree diagram to work out what to do. So crash 1 could be in the week or the weekend, and the same for crash 2. It could be in the week or it could be in the weekend after we've picked the first one. Now the 2 branches of that we want would give just one that occurred during the week. So we want, if we get the first one as the week, we want the second one on the weekend. If the first one was the weekend, we want the second one in the week. So looking at our first branch there, to go in the week, we have these numbers here. So that's 28, 33, 28, 37, and 53 makes 179. So this branch here, let me just grab another colour. Let's go with this one. So this branch, we would do 179 out of 292 for the first crash. Then on the second one, we've got 113, because we worked that out from this first one, that could happen on the weekend, with 291 crashes left to pick from, because we already used one up when we selected a weekday crash for the first option. The second branch, we would have 113 weekend crashes out of 292. Then we have 179 out of 291. And we'll add those 2 branches together to get the overall probability. So we'll go 179 over 292 times 113 over 291. Then we'll add on 113 over 292 times 179 over 291. Gives us 0.4761. I'll just add a little note in there that we've added those because I kind of ran out of room to be able to write the full thing in. Okay, for part B, we want to work out if these 2 things are independent. Now, if independent, then the probability of A times the probability of B is equal to the probability of A and B. So the probability of the first one, so that is evening, so the probability of a crash in the evening, let's go take a look at that. We have 70 as our total out of 292. Then the probability of it happening at the weekend, let's see, the total for weekend, we had that before, was 113. So that's 113 out of 292. Now the probability of evening and weekend. Let's take a look at what we've got up here. Evening and weekend, adding those two together, we have 24. Okay, now let's check. 70 over 292 times by 113 over 292. Let's go decimals here. That's equal to 0.0927. And if we do 24 divided by 292 as a decimal, that's not equal. So therefore, they are not independent. Okay, for part C, we have some conditional probability to compare. We want to know, is a fatal crash involving speed more likely to occur during the evenings at the weekend or the evenings in the week? So let's start with working out each of those probabilities. So the probability of a fatal evening crash, given that it's happening in the week, will be, let's go have a look at the table. So we want all of the evening crashes out of all of the week crashes. So evening total is this section just here. Out of the total for the week that we worked out earlier on was 179. So in the evening, we have 7, 9, 2, 11, and 17. So 46 out of 179. So 46 out of the weekday crashes happened in the evening. Then the probability, let's get another colour, of having a fatal evening crash, given it's a weekend. Okay, so let's take a look for all the weekend ones. That's this here. So that is going to be 24 out of the total for weekend crashes we had from earlier is 113. Now 46 divided by 179, that's equal to 0.25698, and 24 divided by 113, 0.212389. I'm giving lots of decimal places just to preserve the accuracy. And you can see that the week value is greater than the weekend value. So let's write down how much greater it is. So if we do 46 over 179 and we divide it by the 24 over 113, we can see how many times bigger it is. So that's 1.2. So fatal evening, crashes are approximately 1.2 times as likely on a weekday than on a weekend. I just realised I put evening in twice. So fatal crashes in the evening are approximately 1.2 times as likely on a weekday than on a weekend. Okay, for part 2, let's take a look at the table again about why we should be careful with the comparison that we've just made between week and weekend. So if we take a look at this table, we can actually see that while we were doing that split between week and weekend, it puts Friday as a weekday, but we know that actually, really, that's probably what most people would consider the start of the weekend, is to be Friday evening. And that's actually where we have the highest number of fatal crashes. So doing the division that's strictly making Saturday and Sunday the weekend days is not really showing us what's happening. And actually Thursday matches Saturday. So let's put something in about that. And with this type of question, you should support your answer with some calculations as well. So there's how I've written that out. Now let's put in a calculation. Let's do Friday and Saturday together. So if we lump Friday and Saturday evenings together as being the weekend evenings, and Sunday is like a school night, it's not really part of the weekend when we're thinking just about the evening. So let's see what happens then. So if we do a fatal evening, given that it's the weekend where we're counting Friday and Saturday as being the evenings, let's see what we've got there. So Friday and Saturday becomes the evening that we're counting here. And our total weekend crashes are just there. So it'll be 17 plus 11 is 28, divided by 53 plus 65 for those totals. So that's 0.237. And then let's do for the week. So all of the other ones, and I'll just pause while I calculate that. So those evening ones with that one makes 42. And this total with that one is 174. So if we do 42 divided by 174, gives us 0.241. So both of those, if we were rounding to 2 decimal places, would give us the same answer. So these are much closer. Now, there are a couple of different ways that you could approach that problem, and I didn't have an awful lot of room to be able to show different ways of looking at it. There is another option in the answers in the D&D resource booklet that you can look up as well, of looking at the 2 highest likelihoods within the week, not looking at whether it's week or weekend. You can take various different approaches to this type of question. Okay, with part D, let's set this up as a tree diagram so we can see what's going on here. So it could be that it was made by company A or company B. 60% of the components are made by company A. So if you select one at random, you would get a 0.6 chance of it being company A and a 0.4 of B. Then doing the test, 2% of the ones made by company A fail. And then we got don't fail. So this is a 0.02 and a 0.98. And then for company B, the rate of failure is 4%. So 96% don't fail. Okay, now we want to randomly select 2 components. What's the probability that they were both made by company B? So let's just think about picking one component and whether it would be, what's the chance of it being made by company B. So we're working out the probability that we pick company B given that it did not fail. I'll put just this as a fail with a apostrophe there. So I'm taking this from the question as we're randomly selecting a component that did not fail. So there's the condition. What's the probability then that it was made by company B? Okay, so we're doing this just for one component. This will be the probability that we chose company B and it did not fail, over the probability that we pick a component that did not fail. So we always do this. This is the conditional probability formula that's also on your formula sheet. It's the chance of both things happening over the chance of that condition happening. Okay, so for picking B and it didn't fail, we are looking at this branch just here. Oh, whoops, sorry, not that one. Didn't fail. It's this branch just here. Okay, so we will have 0.4 times 0.96. And the chance of it not failing, of getting a component that doesn't fail, will be what we've just worked out as 0.4 times 0.96. That's one way of getting it, but we can also do company A and not failing would also give us one that didn't fail. So that's 0.6 times 0.98. Comes to 0.3951. Now that was for one component. So the probability that part 1 that we pick and part 2 fit this condition, imagine it again like a tree diagram. First tree is that it fits this condition is 0.3951, and then the second one we pick is also 0.3951. So we've got two components. Both of them had this chance of 0.391. So if we were working out that probability, we would times those two together. So if we square that answer, we get 0.1561. All right, for question 2A, we've got some information about the probabilities of having their driver's license in year 13. We've got a few bits of things going on here, and the key thing to note here is that there is a bit of an overlap. So we have this having a full license and owning a car overlaps these two things of having the license and owning a car. So let's think about that as a Venn diagram, a fairly simple one. So the overlap here would be of 0.15 in the middle. So that's full. Apologies, my dog just went nuts at somebody walking by the window. Okay, so we've got that overlap of 0.15. Now, when they're on their full license, the probability of having the full license is 0.74. So we've got 0.74 would be the total for that circle. So we need to take off the 0.15 and we'll be left with 0.59 here. And then owning the car has a total of 0.24. So take off the 0.15 that's already counted in the middle, would have 0.09. So now the probability that a year 13 student has a full license or owns the car is all three of those together. So 0.59 plus 0.15 plus 0.09 is 0.83. Oh, this looks like it's going to be a three-way Venn diagram, which is one of my favorites. So we're going to pop down 3 circles. Actually, I'm going to make that a bit bigger. Always make these as big as you can fit in the space that you've been given. Just makes it easier to work with. Okay, so this is road fatalities, whether they involved alcohol, speed, or driver error. So let's go with alcohol, speed, and driver error to label our circles. Now we're going to work through these bullet points and add them to the diagram as we go. Now sometimes they're in the order in an order that helps, and sometimes it's not. So we might just jump around a little bit. Right, 46 alcohol related means that this alcohol circle is going to add to 46. So we can't put 46 straight in there. Same for these 3 dots actually. So I'm going to look for one that helps me to put something in straight away. Now that's this one just here. 11 were a result of alcohol, speed, and driver error. So all 3. They cross over in the middle, and there's 11 that is all 3 of those. I'm going to tick off the bullet points as I use them, and then keep searching for the next thing that's helpful. So if we look at, let's go with this bullet point here. 9 were a result of speed and driver error, but didn't involve alcohol. So overlap of speed and driver but not alcohol is this space just here. So that's a 9 there. We've got this 14 were a result of alcohol and driver error but not speed. So where alcohol and driver overlaps but doesn't include speed is just here. So that's 14. 4 were not a result of alcohol, speed, or driver error, so that's on the outside. And really, I should actually put a square or rectangle around this. Now, we've used the 4. Okay, let's work back up. We got 22 were a result of speed, but did not involve alcohol. So that would be anything that's in speed but not alcohol, so that'd be that section there. So now we've already got 9 in there, and the total has to add to 22. So 22 minus 9 makes a 13. So we can pop a 13 in here. Okay, now we can do the other pieces. Let's go with the speed total first, because we've got everything in this circle except one little gap. So the speed total is 50. 50 take off 11, 13, and 9 leaves us with 17. Then we can do the alcohol total is 46. So 46 take away 17, 11, and 14 is 4. And then the driver total is 57. So 57 take away 14, 11, and 9 leaves us with 23. Okay, now calculate the probability that a randomly selected road fatality from these involved alcohol and speed. So we want the crossover of alcohol and speed. Out of our total of 95. So that's 28 divided by 95, 0.2947. Okay, part C. A report from this global paint producers found that the chance of picking white for a car is 22%. Calculate the probability the next 2 cars sold in New Zealand will be white. Now let's keep this very simple. The probability of white and white would be the first car is 0.22 times by the second car being 0.22. So 0.22 times 0.22 is 0.0484. Now that's a very simple thing to do, so you would expect the next question, which is 2 assumptions that we're making when calculating that. Now the first thing to spot that when you read this through, this is from a global paint producer, and we're working this out for the cars in New Zealand, so we're assuming that the same pattern holds. And then the other one, there are different ones you can go for. I think the next obvious one, especially when you're doing the chances of 2 things happening, is to say that we've assumed they are independent. Which is to say that if the first car being sold is white, it doesn't change the probability of the second car being white. You could also talk about the distribution of white cars across New Zealand is even and freely accessible to everyone everywhere in the country. And you can also talk about the fact that the proportion of white cars availability needs to stay the same for both of the cars to be picked as white. Okay, so let's set up a tree diagram for part D. We've got that we could pick a car that's either diesel or petrol for the first one, and the second one also would be diesel or petrol. Now we will have to work this out in algebra because we're not told the total number of cars, only that there are n, but we are told that 2 only 2 of them are diesel. So we have 2 out of n for the diesel cars, and the rest of them would be n minus 2 out of the total of n for the petrol. Now, if on the first car we've picked one of those diesel ones, then we only have 1 diesel one left on the next branch. So we'd have 1 over n minus 1, because we've subtracted 1 from the total, having bought that first car. And the petrol cars here remains at n minus 2, the same as we started at for the first choice, but we have 1 less car in total to pick from. So it's n minus 1. Okay, now if we picked a petrol car first, we would have 2 diesel cars left out of a total of n minus 1, and we would have n minus 3 petrol cars left, 1 less than the n minus 2, over a total of n minus 1. Now we want the probability that exactly 1 of the cars driven away is diesel. So exactly 1 being diesel would be this branch here. If we do diesel, then petrol, or this branch here, petrol, then diesel. So the probability of exactly 1 will be 2 over n times n minus 2 over n minus 1 for that top branch. And then we'll add on n minus 2 over n times by 2 over n minus 1 for that bottom branch. Now it might be enough to leave the algebra like that, but I am going to tidy it up just in case we might need to. So this would be 2 times n minus 2 over n minus 1 plus 2n minus 2 on the right over n minus 1. So if we're adding those two things together, they are actually the same thing. So we'll have 4n minus 2 over n minus 1. Okay, for question 3, we have a game being played where 3 cards are turned over and then added up, and these are the totals of those cards. And this is after 36 times of doing it. So we want to use the experimental results, meaning we have to use what's on the graph here to estimate the probability of the total of the 3 cards being greater than 4. So the probability that the sum is more than 4, well, we've got 36 in total, and there is just 1 that's not. Oh wait, more than 4 means we've got to do the 5 and 6 together. So that'll be 12 here on that line, and that line here is 5. So 12 plus 5 is 17 out of 36. One thing I forgot to point out that we need for the next bit is that we're just playing with the 4 aces and the 4 twos. So we have 8 cards in total, 4 1s and 4 2s. Okay, let's look at part B now. Explain the theoretical probability of getting a total of 4 with the 3 cards. So to get a sum of 4, we could do 2 1 1, 1 2 1, or 1 1 2. Now the probability of each of those, to get a 2, we're talking about that half of those cards are 2s. And then to get a 1 after that, well, 4 of them are 1s out of the 7 that are left. And then another 1 would be to get, if we've used up a 1 and we've got 3 left out of 6 cards. Similarly for this line here, it'll be a half. Then we've got 4 out of the 7 for the 2s, and then we've got 3 1s left. Half, 3 1s, and then 4 2s. And we will add those all together. Actually, let's write this as, so the probability of getting a sum of 4, well, one of these is 1/7, and the others, you can see the numbers are the same. We're timesing across, they're just in a slightly different order. So all of them are going to come to 1/7. If we add them together, we get 3/7. Now the experimental result gives probability of getting a sum of 4 as being, so exactly equal to 4 was 18 out of the 36 shuffles. Now that's exactly half, that's 0.5, and this one here, 3 out of 7, is 0.4286. So the result from the experiment was slightly higher than what we would theoretically expect, but that can happen due to natural variation within experimental probability, and we only had a fairly small number of trials. So there's my write-up of that bit. For part C, thinking about a model versus an experiment. So an experiment is where you actually run the trials, whereas a model is you just think about theoretically what it should come out to. So let's write that down first as what the differences are. And then we'll say what assumptions we would need to make for setting up a model. So when making this model, we would first assume that it fits the purpose of what we are trying to model. The outcomes are independent. And one thing that I forgot to do, try to always put this into the context of the thing we're talking about. So it fits the purpose for drawing cards at random. The outcomes are independent to represent the independent cards being drawn. The probabilities are equal for each of those cards, representing what we've got in the situation. Right, for part D, we're filling in that theoretical probability distribution. So let's start with the probability that the sum is 3. Well, there's only one way to get that. That's that we've got a 1, a 1, and a 1. So that'll be 4 out of 8 cards, 3 out of 7, and then 2 out of 6. So 4 eighths, 3 sevenths, and 2 sixths. That makes 1 out of 14. So we've got 1 over 14 in here. Next, let's look at how we could get a total of 5. Okay, so to get a 5, we could do a 2, and a 1. We can get a 2, a 1, and a 2, and then a 1, a 2, and a 2. Okay, so 2, 2, 1, we'd have 4 out of 8, 3 out of 7, and then 4 out of 6. And similarly for the other ones, so I'll just fill those in. So that also comes to 3 sevenths. And then to get a sum of 6, we'd have to do 2, 2, 2. So there's only one way to do that. That'll be 4 eighths, then 3 sevenths, and 2 sixths. Same as what we had for this one just up here. I just switched colours to make that easy to reference what we're doing there. So we've got a 1/14 in that final one. Okay, calculate the expected mean from the probability distribution table in part 1. and compare it with the experimental results at the start of this question. Okay, so expected mean is the expectation of S. So that's 3 times 1 over 14. 4 times 3 over 7. What I'm doing here is taking the value and timesing it by the probability of it happening, and then adding that all up. That is also on your formula sheet for how to work out expectation of a value from a probability distribution table like this. So now let's just add them all up. And we get 4.5. Then we want to compare it to the experimental results that we had at the start. So the experimental one we'll do in the same way. So let's take a look at what we're looking at with the probabilities up here. So we'll do 3 times, well, that probability there is 1 out of 36, plus 4 times 18 out of 36, 5 times 12 out of 36, and then 6 times 5 out of 36. Which is very similar to the theoretical probability. So the means are similar, but another thing we can spot in that comparison is that those values are not so similar. They're somewhat close, but not really that much close because of that sampling variation idea. And we know that sampling variation has more of an impact on smaller sizes of that experiment. So because this has only got 36 trials in it, this is almost certainly just down to sampling variation. And that's the end of that paper. If you found that helpful, please like and comment, interact with the video because it helps other people to find it too. And you can go to my homepage and find the playlist that contains the other worked solutions for these practice external assessments from D&D, as well as some worked solutions for the past papers for the NCA exams and some tutorial videos. If there were any parts of this that you didn't quite follow, you can go back and relearn them. All right, thank you and see you next time.